Hi everyone, welcome to the channel. Today we're going to create a fully procedural ice path formation effect inside Houdini. We're going to use a couple of really cool techniques to achieve a fully scalable system that we can easily adjust to the production needs. So let's actually take a look at what we are going to be creating. Alright, so let's create a new geometry, and here we need 2 points, so let's use the add nodes. We can make a copy, and the first we can call it the source, and the second will be the target. And here let's add 1 point, and here the second one, but let's change the Z position to maybe 5 for now. And so let's zoom out. So you can see the one is here and the second is at the center. So now we can draw a rectangle, and let's connect the source to the first input and the target to the second one. Let's display the rectangle, and now let's press Alt E to bring this window for Vex code, because we're going to type quite much of it. So yeah, maybe let's keep it like that. And yeah, let's start. So first we need a vector. Let's call it target pose, and here we want to store the position of our target that we already created. So let's use a point function, and we're going to take attribute from first input. We want position of point 0, like this. And now let's create another vector, which will be vector to target from source. So let's call it to target, and let's subtract target position v at p, like this. Now we can go next, and we can make a direction from this vector. So another vector, direction to target, and let's make it equal to normalized vector that we already created above. So to target. Okay, so next we need a distance. So float distance to target, and we need to calculate the length of the to target vector, like this. And yeah, we can preview the normal, how it looks like. V at n equals there to target. Let's hit apply, and let's preview the normal. So we can see that this is our source point, and here if you display, this is our target. So now the basically the direction to target stores this direction that you can see that is previewed on the normal. So let's proceed, and now let's create a new float. Let's call it duration, and let's use a channel parameter integer, and let's call it simply duration. And with this parameter we will be manipulating like how long does it take for the path to reach the target point, basically. So let's go and create a second float called controller offset, and let's use a fit function, and we're going to fit frame that will go from 1 to duration, and we want to map this to go from value of 0 to 1. And then we are going to create a controller. So vector controller equals, we need to interpolate between position of the source and target position. And as an interpolator, we are going to use the controller offset, like this. And yeah, now let's specify the resolution of our path, something like the base resolution, how many basic steps we want to have for the main path. So to do this, we need to create an integer variable. Let's call it steps total, and let's create another channel parameter for it, and let's call it steps total. And next, let's create another integer called steps maybe step scatter, like this, and another channel step scatter. We're going to use this variable to scatter some points for every step. So this way we will have like nicely procedurally generated distribution of the points along the path. So you'll see later how it works actually. And to mix this, we need a step offset variable, and let's divide the distance to target by steps total. So this way we can calculate how we can basically calculate the distance between each step by doing this. And yeah, so now we only have these 2 points. Yeah, we have source and the target, so we need to populate the path. We need to construct the path between the source and the target. So we need to create a for loop. Let's start counting from 0, and how many we want basically as much points as there is steps. Yes, yeah, we need to, we have scatter. Yeah, we need to, after scatter, we need to create another variable. Let's call it steps current, and let's convert to integer steps total times controller offset, like this. So we will be able to dynamically construct the path from as many points as we need at the current controller offset position. So here let's specify a condition if I is less than steps current, like this, and let's increment by 1 after every loop. And here let's create a new vector position v at p plus iteration times multiplied by direction to target, and let's multiply it with step offset, like this. And next let's create another vector called next pose. This is interesting because we are going to use this to to calculate what is the next what is the position of the next point after this iteration. This will help us a lot. So v at p plus I plus 1, like this, and now we can multiply it by this. We can copy and paste here. So basically we are doing the same, but for the next iteration. And let's create an integer variable called path pt, and inside this we are going to store the reference to the point that we are going to create. So at point 0 we want to create this at position like this. Let's hit apply. We have some errors, steps total and steps current. Yeah, here is the problem. And of course we haven't created the channels like this. So we have a small typo here. It should be controller spelled properly. Now if you click apply, you don't have an error. And if you go here to the parameters, let's say for duration we want to have like 48 for example, and for steps total maybe 15, and step scatter like 5. Step scatter won't do anything for now anyway. And let's see why it doesn't work, because we should see some points here. So another typo here, it shouldn't be framer, it should be frame like this. So let's apply, and now you can see how it works. So basically you create the path dynamically based on this duration parameter. It specifies how many frames does it take to construct the path that goes from the source to the target. So if you do like 12, it will be really fast, and so on. So I will leave it at 48 for now. And yeah, let's proceed to work on the scattering actually, because we have the main path for now, and we want to make it more interesting and give it more randomness. So let's make a space here, and for that we need another loop. So we need to nest a loop inside loop. So let's call the counter j equals 0, and the condition will be if j is less than step scatter, and let's increase by 1 like this. And here we need another float called normalized loop index, and this will store like all the loops, but this value will be mapped to go from 0 to 1. So let's use a fit function. We're going to fit j, and it goes from 0 to step scatter -1 here, and we want to map this, as I said, to go from 0 to 1 like this. After this, let's create another float. Let's call it side random, and let's round the number of randomly generated float like this. And then let's fit this value. Side random equals, let's use fit 0, 1 because it goes from 0 to 1, and we want to fit itself to go from -1 to 1 like this. And now let's create the vector called side direction. We are going to use this variable to control, how on which side we want to push the scattered points. Some will go, to the left, some will go to the right, and that's why we calculated these random values here. This will be like the dictator for that. So let's use a cross function, and let's construct the vector here, 0 for the x component, side random for the y component, and 0 for the z, and another vector will be direction to target like this. Okay, let's make a space here, and now let's create the next vector called offset direction, and let's make it equal to side direction for now. Another float, scatter range. And for scatter range, we're going to create a channel parameter. So let's call it simply scatter range. With this value, we will be controlling how much point we want to scatter per every step point here. So it will be similar to resolution of the details of the scatters for the path. So that's how it works. Next, we need a vector called neighbor offset. We are going to call the scattered points the neighbors, and the main will be like the steps. So something like that. Let's make it equal to offset direction multiplied by scatter neighbor offset. Yeah, offset direction, let's multiply it by scatter range like this. But before, let's maybe go to the scatter range and let's also multiply it with fit at random value. So let's use fit 0, 1, and we want to fit random value generated from j multiplied by I, and we want to fit it to go from 0.01 to 1 for now. Okay, we have neighbor offset, and after neighbor offset, let's create new float called next pose lerp, like this. We are going to lerp, we are going to scatter some points. Let's say we want to scatter some group here, and we're going to use this value next pose lerp to to smoothly distribute scattered points between the current point and the next one. So float next pose lerp, let's make it equal to random value generated from j multiplied by I, and let's multiply it by channel float, let's call it smooth distribution, maybe like this. And another vector, neighbor pose. This will be the position of our neighbor. We are going to interpolate between position of the step point, next step position, and we are going to use next pose lerp value as an interpolator, like this. And to that we want to add the offset, so neighbor offset. Okay, so now we can go ahead and let's create the vector neighbor to target, and let's make it equal to target pose minus neighbor position, like this. Okay, so we have it. Now let's make a distance, so float neighbor dist to target, and we're going to calculate simply the length of this neighbor to target, like this. Okay, and now let's create a normalized distance, so float n distance to target equals fit. We're going to fit neighbor dist to target that goes from 0 to distance to target, and we're going to map it to go from 0 to 1. Okay, we have it. Now let's create update the neighbor pose variable. So neighbor pose equals we want to actually subtract, so minus equals neighbor offset, and let's multiply it by this normalized distance that we created, so nDist to target, like this. Okay, so we have this. Now let's make some space here and let's create another vector. Let's call it neighbor to controller. Maybe this will be the vector between neighbor and controller. So we have some scattered points here, and we have also our controller. Controller is the main interpolator, that is driven by the frames that I already showed you. So neighbor to controller, let's make it equal to neighbor pose minus controller. And here we need another float. Let's call it neighbor distance to controller. So we need to calculate the length of this vector. We can copy and paste. And after this, what do we need? We have this, we have that. We need another float. Let me think. Yeah, let's create an influence range. So float, we're going to call it controller influence range, for example, and let's make another channel and let's call it controller influence range. So with this value we'll be able to control some other values like the spread of the lines and so on, based on the distance the current point is from the controller, like this. So we have this, and now let's make a normalized value from this. So float normalized influence range. Let's make it equal to fitted value of neighbor distance to controller, that goes from 0 to controller influence range. And let's remap this value to go from 1 to 0, so it's kind of inversed. And here we are. Now let's make some space here. Let's create another float, main direction interpolator. So we're going to interpolate the direction of the line based on this value. So we need to fit the basically inversed normalized distance to target. So we need to use an absolute function, and here we need to subtract the end distance from the 1. So end distance to target, like this. And we want to map this to go from 0.35 to maybe 0.1 or maybe 0.75, like this. And here another vector, neighbor direction. So it's actually we're getting close to it. So normalize, we need to normalize the interpolated vector between the up vector and direction to target. So let's use a lerp function, and we're going to lerp between the up vector, so 0, 1, 0, and direction to target. And we're going to use let me think, yeah, we're going to use main direction interpolator like this. So let's create another variable. Let's call it meld lerp delay. We're going to create something like meld simulation, something like that. It's not physically meld. I just called it in code like this. It's basically like the rotation of the lines during the creation. We're going to slightly rotate them to the ground, like some kind of gravity. And so let's use a fit function, and we're going to fit a randomly generated number. Let's maybe multiply I with j, and let's add some random value like 2, maybe like this, and let's fit this value to go from 1 to 1.1. So it's a small window, but it will do the job, you'll see. And let's multiply it by duration, actually. Duration, like this. So we have meld lerp delay. Now we need the lerp itself. So float meld lerp equals fit. We're going to fit the frame to go from 1 to meld lerp delay. And we want to normalize value, so 0 to 1, like this. So now let's create a parameter for maximum rotation, so we can easily control that. So float rotation max, let's make it equal to float channel called rotation max, like this. And let's multiply it by we have it here, side there. So side direction inversed, actually. So this is what I was talking about previously. Some of the lines, thanks to this randomization, will be able to, you know, rotate toward this direction, and some will go to this direction. So let's go ahead and let's create a rotation, actually. So float rot, and let's convert to radians. Let's convert rot max, and let me think. Yeah, rot max multiplied by normalized loop index, and this, let's multiply this by meld lerp, actually, like this. Okay, and now let's update the rotation. So rotation multiplied by equals we're going to multiply by inversed normalized distance to target. So 1 minus n dist to target, n dist to target. And now we need to create the vector 4 variable. So vector 4 neighbor quaternion, because we are going to create a quaternion, and let's use a quaternion function, and here let's use a rotation that we already created, and direction to target as the axis for our rotation. So now we can actually rotate our neighbor direction. So let's update neighbor direction. So let's use a q rotate function, and we're going to use neighbor q as a rotator, and what do we want to rotate? We want to rotate the neighbor direction itself, so neighbor direction like this. Okay, so we are really close to the end, so let's make some space here and let's make another variable called height max. With this value we'll be able to control the height of the lines actually, so with some randomness. So let's actually implement this. So we need another channel for that. Let's call it height max, and let's create another variable called height, and we're going to use again fit01 function to fit the value of randomly generated number, like random maybe j plus 4, maybe multiplied by I, like this. And let's map this to go from 0.1 to height max. And after this, let's multiply it by inverse, normalize this to target, so absolute value of 1 minus n this to target. This should be minus actually. Yep. And here let's update the height. So height multiplied by equals, again we can, yeah, let's make the inverse of, let me think, normalized influence range. So absolute 1 minus n influence range, like this. Okay. And next we want to actually finally calculate the end of the line, the final position of each line. So we are going to call it tip pose, and this will equal to height multiplied by neighbor direction, and we're going to add this to neighbor position, like this. So we have tip position. Now we can go ahead and we can create finally the points. So integer base equals add point 0 neighbor position, like this, and another point for the top, so integer top at point 0, and let's use the tip pose, like this. And finally we can connect these 2 points with the line, so add prim 0 polyline base. We want to connect the base with the top, like this. Okay, so now let's click apply. Let's see if we have some errors. Yeah, of course. So it actually looks like I skipped the equal signs on some variables assignments. So here for n loop index, and I can see it here too, neighbor dir and main dir interpolator. Let's see. Another issues 4593. We have another typo in neighbor direction calculation, so I forgot to close the braces for lerp function, so we need to add this. And another is 47. And I also forgot to make an equal sign for melt lerp delay variable. We have another typo in melt lerp fit function, so after 1 we need a comma. And if we apply this, now we need to go a little up, and here controller influence range, we need a small letter like this. And after these changes it should work actually, so we can take this back for now, and let's actually create the parameters for our channel functions right here. So let's experiment with those values so you can see how all of this works. So duration, steps total, we already told about this. Well, now we have step scatter, so this will control how many points we have scattered per every point. So we want to make a bigger range like this, so you can see that we are spreading the scattered points across this perpendicular line. But together with this, we also have this smooth distribution, so we can lerp between current and lerp steps. So if we do this, you can see how it works. But what's important, let's increase the height, because that's the core point of this. So some properties we already coded. It's like we have this progressive height level that goes up, as well as the rotation. We need to set rotation, so maybe let's set it to 90. And you can see that by manipulating this rotation value, we are spreading them from the main path. So another cool thing is that this is this variable that we used, this normalized influence range. So thanks to that, you can see that if you play this, we have this smooth transition, this smooth rotation. So when the controller goes, it also spreads those lines a little. So you can really combine these values. Like maybe you can even make something bigger, like 240. So you will see more of this, like that. And you can actually control the influence range by this parameter that we already created. So this is cool, because if you change this to maybe 1.5, you can see that you also have this growing effect. And this is the this influence will also affect the rotation. So you can see. So we have like the base functionality for now. We have something that we can build on top of, so we can now proceed and create the mesh from it actually, and you will be able to always come back to these and change these values, as well as some of the values that we already coded here, because we don't have a channel operator for everything. So you can experiment with some values here, and you can always change and see how this affects the final outcome of this base system. So yeah. Okay, so now let's go to later frames, like here. And actually we have only 2 points per line for now. Maybe let's increase the height to go like maybe 1.5, like this, and let's use a resample node on this to to add more resolution to this. And maybe let's use the length of value of 0.05, maybe 0.25. And after this, let's create some irregularities for this. So we are going to use a attribute noise for that, and we want to apply the noise to position parameters, so P, and let's use a 0 centered value, and this is too much, so maybe let's play with the values, but let's decrease the amplitude. Something small for now. We can always change this, but we don't want too much of it here, because you can easily exaggerate that. I think it's too much, so something really subtle like this. It's important to keep this in mind, that after applying attribute noise, you can also slightly move them away from the ground, so don't apply too much of it, because we haven't implemented any functionality for this. But you can, of course, you can take the base point and you can always manipulate the influence of it. But I will leave it like this for now. So after attribute noise, maybe actually before it, let's create a wrangle node, and we want to slightly bend these lines. So after resample node, we need something like a curve view attribute. So let's check this box here, and you can see that in geometry spreadsheet now we have this attribute here that goes from 0 to 1 respectively across along the line. So let's actually use this to bend these lines a little. So let's update the curve view attribute. F at curve u equals, let's inverse it for now, so absolute value of 1 minus f at curve u itself. And now we are going the z direction for it. You know, this is really important here, because I won't be implementing any logic to go along with direction for now. So if you want, you can, but I will like hard code it here. So this basically depends on the direction that you specified your target position. So for now it goes on the positive z axis. So I can update the z position. So v at p dot z minus equals, and here we are going to multiply curve u attribute 3 times. So Control C, multiply by curve u, and multiplied by curve u once again. And then we want to subtract curve u multiplied by 0.5, like this. So you can see actually we have a little band. You can actually disable it if you don't like it. It depends on your needs. And after that, because we already inverted the curve view attribute, but we need the original value, so f at curve u equals, we are going to invert it again. So Control C, Control V, like this. And we are done here. We can go to the next step. So now let's organize it a little, and here we can drop another wrangle node after the mountain, after the noise node. And here let's inverse the f curve view attribute. So we can copy and paste it, and now we are going to fit this to go from, because we don't want to go for this to go from 0 value. We want something a little bigger. So f at curve u, we are going to clamp this value itself to go from 0.01 to 1, like this. You know, just to avoid the 0 values on the lines. So now we can drop a polywire node to actually add the volume to these lines, and after this we can drop a normal. And yeah, and here in polywire let's play with some settings. The values that work for me is actually 0.1 for wire radius, and here we can actually use the attribute, and we're going to take the scale from curve u attribute itself. And other values that I've changed is like the divisions. I've made 12, and I think I will leave it as it is. You can use another values, but I won't spend more time on it. Let's proceed to the next step, which is we need to create a VDB from this. So VDB from polygons, and we are going to use distance, yeah, and voxel size. Maybe you need to play with these values. I will leave it at 0.01 for now. And now maybe we can, because you can, it looks like this, that you can jump between this node and changing the settings here for now, because before you actually proceed with anything, it's a good idea to actually have some shape of it, so you can play with these settings here and make something actually that looks good. So I will set some values here and I will be here in a minute. Now let's proceed and let's smooth this VDB a little. So VDB smooth like this, maybe 3 iterations, like so for now. We just want a basic shape for now. We will focus on the details later. So we have a smooth. Now we need to convert this to the polygons. So VDB convert like this, and we want to convert to polygons. I will leave it as it is for now. And yeah, now we can go ahead and we can create a new material. So let's go to the material palette here, and let's drop a principled shader. And now let's jump to the material network, and here let's call this shader ice. And going back to the object, we can assign this material here. So let's use material node, and let's apply this material here like this. So we have a material, and now we can make some previews of how it actually works. I will make a quick sketchbook to show you the idea. So here you can see how it actually looks like. It is cool because you can easily go right here and you can change the duration of it and everything, as I said before. But for now we need to make some basic scene setup. So let's create the camera, and I will choose the angle like this, maybe something like that. And we also need some lights, so let's create a distance light, and here you have your camera. So I want the distance light to go something like 90 degrees from the camera direction, so maybe like this for now. And we also want some environment light, so let's drop another here. And apart from that, I think it will be cool to add some area light, something like here, so we will see some lights scattering on the edges of the spikes. So maybe like this, maybe here, maybe like this. And we can add another area light to lead the object from the above a little, like this. Now we need to go back to our setup, and here we need to create some attributes to control our shader, our material. So we need basically 2 or 3 properties, and I think that first we're going to take basically the curvature. So after the conversion, let's drop a measure node, and we are simply going to measure the curvature like this. So we can apply different effects to those red areas and differentiate everything from the blue one. So yeah, we have the curvature. Let's connect it here, and now let's go to the attribute noise here, and let's drop a wrangle. We are going to simply extract the endpoints of each line. And how we can do that? Well, because we have this curve view attribute that goes from 0 to 1, so we can delete everything except the 1 values. So this will give us only the top points. So let's actually do that. So we need an if condition. If f at curve u is not equal to 1, we are going to remove everything. Remove point 0 at point number. So if you preview the points, you can see that these points are actually the tips, the endpoints of each line. So it's kind of cool. We're going to use this to transform some attributes. So let's add some color here, and let's make it red. What's really important here is in all those colors that we are going to set here to transfer these attributes, use whole numbers for each component. So it's really, you know, important to not have like 0.5 or something like that. You need a 1 in one component and 0 for the other. So then we can go here and we can actually do an attribute transfer, and we can transfer this color here, but we can play with the conditions here. Okay, so for distance threshold we can use a value of 0.04 maybe, and blend width something small, maybe 0.08 or 0.5. But let's drop a color for the main object, so let's make it green. 0, 1, 0. So we can see what's going on maybe. Yeah, I think it's okay for now. We will change it later. So now we can create another attribute. So before the resample node, let's drop another wrangle node. Actually, we need to create an add point. So let's connect it to the first input, and this will go to the second one. And here we need to create this point actually. So let's click this plus. And here, basically, we want to drive this point based on the position of the controller from this code. And basically, the controller doesn't exist physically anywhere here. It's just the value that is controlling the interpolation between source position and target position. So we need to extract it somehow. And here you can see this is stored right here. So the way we are going to do this is simply we are going to create an attribute called controller of type vector, and let's assign the controller value to it like this. And now we are going to grab this value here. So v at p equals, we're going to get the controller attribute. It may be from point 0. So now if you preview the point, you should see that the point is moving accordingly to the controller that you set here. So this duration that is controlling how the path actually grows, you can see, because you can change the duration to maybe 24, it will go faster. And this point will also follow this movement. So you can see the beginning is here and the point is here too. So I will change this back to 48. But having this point, we can now make another color transfer to to control another cool shader effect. So let's drop a color node here, and we're going to make it blue. So 001 like this. And now we can go down and we can create another attribute transfer, and we are going to transfer from the controller itself like this. Maybe let's go back to this, and let's change the source and destination to points, and just to be accurate, and let's deselect the primitives, and in points we only want to transfer the color. So actually you can copy and paste this and get rid of that, so we don't have to do it, you know, twice. So we have this, and now actually if you preview it, it looks like this. But let's go to the later frames. You can already see that at the beginning, at the front, we can see that you already are transferring some colors. So we can experiment with the values here. So maybe I will use something like 0.25, and for blend, I don't know, something like 1.1 maybe for now. And we are going to use these colors actually to create a masks for the shader itself. So it won't look like this, like we won't have red, green and blue and, you know, all these colors in our eyes. We are going to separate these colors to create the 0 to 1 values that will control our shader. So let's actually do that. Let's drop a wrangle node here, wrangle. And inside the wrangle, let's create a float, and we're going to call this maybe controller mask, for the mask that is, you know, driving this front part of the object. So let's make it equal to v at cd. We want to only get the blue color, so it's the z component. And another mask will be tip mask for the individual tips of the lines. So we are going to take the red color, so it will be X component, like this. So we have these two masks, and we have also the curvature from here. So now we can drop a null node here, and we can call it out for now. And now we're ready to jump to the material network and experiment with everything. So let's take a look from the camera view, and before that let's actually make some good shape of it. So I will leave controller, I will leave the duration for now as it is, and for steps total I will use the value of 100 as it is, and scatter range maybe I will use something like 0.25. And for smooth distribution I will leave it at 1, but step scatter I will scatter more of it, so maybe 15, like this. And controller influence will be 1, and rotation max I will leave it at 120, like this. So I like this, but height, for the height I will double it, so I will make it 3. Maybe too much, maybe 2. Okay, and for VDB, let's go here, and yeah, I can leave it at 0.01. So let's jump to the render view to see how it actually looks like, and let's jump to the material network. So first we can turn off the use point color here. and we can start from importing our attributes. So we need an bind node for that, and first we're going to import the curvature itself. So we have a curvature, and if you connect this to surface base color, you can see already how it affects the mesh. So we can actually use this mask to mix between two colors. So let's create a constant node, and let's change this to color type, and let's make it, you know, slightly blue, but something really light like this. And let's copy and paste here, and this one will go to more greenish like this maybe, but really light values like this. And now we can drop a mix node, and we can simply mix between these two and use this value as an, you know, interpolator. So you can see something like that. I think we can go back to the light and maybe change this light that is above to, you know, have maybe 0.5 intensity, and environment light maybe 0.5 too, like this. And yeah, I think it's good for now. Let's go back to the material, and here we can also go and change the IOR to maybe 2. And for roughness, actually we can take this curvature and we can clamp it to go from 0.2 to 1, and we can connect this to roughness actually. So roughness here, roughness, as well as we can use another clamp, and maybe instead of 1, let's use 0.8 for the max value, and we can connect this to transparency like this. But maybe let's go back to the to our setup, and let's actually change these values a little. So here, where we are transferring this, I think we can go to the conditions and, you know, change it a little, maybe something like that, to have some bigger values, to have more red basically, maybe 0.8. Yeah, let's go to the camera and let's see how it actually looks like. Point 2 maybe. Okay, I will leave it at 0.1, but yeah, I think it's okay for now. Let's go back to the network. Okay, now let's actually add another color for transmission. So maybe something more bluish. And now we can import this another attribute. So we can copy this bind node, paste it somewhere here maybe, and it was called tip mask, as well as the controller mask. Controller mask. So now we can add them together here, and we can use a clamp node, and we can clamp it to go from 0.2 to 0.3, and we can use it to control the emission intensity actually. So we can go here and connect the emission intensity, and now we also need an emission color. So let's actually copy this here nodes together with the mix. Let's paste it here, but for the controller we are going to use the tip mask only. So let's connect it to the bias, and let's connect this mix node to emission color. But let's actually change the colors a little. Maybe this, and I don't know, like this. I've noticed that we are actually, you know, in my case I wasn't displaying the final node, so the output was slightly different. So now we can actually work on this. So maybe let's experiment with the emission color. For now, I think that there was too much green here. So let's maybe change this to something more blue, but a little lighter, like this maybe. And also this controller, we can add a little more blend to the controller. So let's go back to the object here, and here in the transfer from controller we can increase this to maybe 1.5 or 1.85, so this bluish area is a little longer. And maybe here we can experiment with this too, maybe 0.05. Yeah, so we have more variation here in these areas. I think it looks cool, like this. Okay, so let's back to the material, and here I will only add, basically I can copy the constant. I will add the value for the code here, and I will make it 2, for example. And yeah, this is the basic setup, really basic, and I will leave it to you for now. You can experiment with this, you can improve it. I won't spend any more time on it, but you can definitely add more features, you know, experiment with this. At this point you can also go back to the object level, to our setup, and you can, you know, play with these settings to shape the object however you like. You can, for example, change the step scatter to maybe 45 to add more points to it, and you can combine it with changing the wire radius to something smaller like 0.05, so you will have more details. And yeah, I think it's all from me, so thanks for watching and see you again.